Every time you're like, oh, you want to go home, make yourself not feel so bad, here you go.
So it's yeah. Right, so great. You are great. You're ready with everything. So you want to switch slides using this thing or?
No, I'll probably just use that so I don't
okay.
mess anything up. Is there a laser?
A laser, yes. This is a simple one.
Yeah,
I'd
rather. I much prefer that.
Okay, that's a simple one.
In Massachusetts.
Okay, so are you able to put it on the screen? Okay, great.
Do you want to announce the beginning of the undertaking?
Okay, let's yeah. Right. So yeah, a couple things. First, we have a change of the chair in training purpose. Ashwin is going to graduate soon. Ashwin is our student at George Washington, and so we decided to do some training activities. So he's going to be a chair now for this session until the coffee break instead of me. And the other thing I wanted you to ask, we are going to do some planning for the happy hour after we are done with the talk. So how many of you, who wants to go for a happy hour in some nice bar? Raise your hand. Let's see. 1, 2, 3, 4, 5, 6. Maybe 7. Are you going for happy hour today? No?
Oh, yeah.
Yeah, okay, 8. 8 people, just 8 people. Come on, there is, okay, maybe 9. Okay, I see. Thank you. Ashwin.
So we'll begin our afternoon session with an invited talk by Jolene Karlberg from the Department of Terrestrial Magnetism at the Carnegie Institution for Science.
Great, thank you very much. So I was asked to give a talk today overviewing the field of exoplanets, which is quite a very large field. So I decided to focus on an almost purely observational perspective because I think it's really observations that's driving the field of exoplanets right now. And so what you're watching is just a movie showing the orbits, a gallery of recent release of confirmed exoplanets by the Kepler spacecraft, which you'll be hearing a little bit more about. So I think it's safe to say that the field of exoplanets, which is now a few decades old, has really transitioned from a field of pure discovery to one of characterization. So we've been able to do more than just count the number of planets that we're finding, but begin to talk about the type of worlds that they are. So you've probably seen and heard of the news announcements of things like lava worlds that we found, of mega-Earths, of clouds on exoplanets. And if you read the literature in this field, you'll even see that people are considering things like water cycles between the core and mantles and oceans in these planets, whether or not they have plate tectonics, what their climates are like, and all sorts of different things. So the general overview of what we'll be talking about today is I want to spend a brief amount of time telling you exactly how we find exoplanets and what you can expect from these techniques in the future, before then talking more about the exoplanets themselves, in particular focusing on the characters of the planets themselves and the orbital architecture compared to the planets in our solar system. And then finally, I'll end with some unsolved questions in the field. There are two general classes of the ways that we find planets. One is to find the periodic signatures of the planetary orbits. And one of the things you need to keep in mind is that although we tend to think about planets going around stars, the physical picture is that both the planet and the star are orbiting the common center of mass. So the star is also moving in this picture, and we can take advantage of that. So I'll be talking about these techniques in more detail, and I just want to briefly mention a few of the non-periodic techniques. One is direct imaging, which is a sort of simple idea of you go and look for a planet. Conceptually simple, technically very challenging because you have a very, very bright star sitting right next to them. And so this is the discovery image of directly imaged exoplanets, and you can see that the starlight, blocked out to the best of our ability, still leaves a lot of residuals, as bright in some cases as the planets that were discovered. So it's a very challenging thing to do. And you'll be hearing more about the direct imaging technique, I think, in the next talk. And then also I want to mention there's microlensing, a way of detecting planets as well, but I unfortunately don't have time to talk in more detail about that today. So one of the periodic methods is that of the Doppler technique, or the radial velocity technique, which early on in exoplanets was the best way of finding planets. And there are many groups who are working on this, and I'll give a shameless plug to a project at my institution, simply because the PI, Paul Butler, was one of the pioneers of getting this technique to work. And this technique works on any stars that are cool enough to have many spectral lines. And the way it works is that you have the star that's orbiting the center of mass due to the presence of an unseen planet. And as the star goes around the center of mass, the light from the star gets blue shifted and red shifted as it moves towards and away from you. And so when you measure the velocity of the star, you see a periodic variation in the velocity. You'll note on the scale here, this is in meters per second. The precision that we can attain today is somewhere between 1 and 3 meters per second, which, to give you an idea, is about the pace of a very fast walk or a slow jog. So that's how precisely we're measuring velocities of these stars. And the future of this project is really just to keep on going and try to do everything better to really try to push our observations to longer period planets and to smaller planets. But I also want to point out that there are efforts to move from the optical into the infrared because our nearest neighbor, M dwarfs, which are very common, are quite faint in the optical and much brighter in the infrared. The second periodic signal that I want to talk about is that of astrometry, or the precise measurement of the positions of stars. And this works in a bit more straightforward way in that you see the planet actually wobbling on the sky due to the orbit around the common center of mass. And the great thing about this is that you can get a signal for all orientations of the orbit, as opposed to the radial velocity technique, which requires you to have some motion in and out of your line of sight. Another great thing about this is that if you can combine it with radial velocities, you now have three-dimensional information, because the astrometry gives you sort of up, down, left, right on the plane of the sky, and radial velocity can give you it's a third dimension. And this method is also more sensitive to planets that are orbiting at greater distances, because the star will then subtend a larger circle on the sky. Radial velocities, on the other hand, are more sensitive to close-orbiting planets. There are a number of ongoing surveys right now, but unfortunately none have successfully detected a planet yet by astrometry. But what we have to look forward to is the Gaia spacecraft, which was recently launched and is expected to detect many exoplanet systems with this method. The last periodic signal I want to talk about is that of transiting planets, and this is sort of the new technique that has recently taken over in finding planets. And the way that this works is you stare at a large number of stars in the sky so that you can get a chance of seeing an orbit that is nearly edge-on, so that when the planet orbits, it will occasionally come between you and the star, blocking out the light periodically. So Kepler is the big winner in this. This is the spacecraft mission that was designed to look for these planets, trying to find an Earth around a sun-like star. And the great thing about transits is that you get a wealth of information. So here is an example light curve where the star is staying more or less constant until a planet passes in front of it. And the depth of this transit curve right away gives you the ratio of the area of the planet to the area of the star. So if you have some idea of how big your star is, you immediately know how big your planet is. And then, if you can combine this with radial velocity, you can then get a measure of the mass. And since you know that this is an edge-on system, or else it wouldn't be transiting, that mass measurement is a true mass and not a minimum mass. So now all of a sudden you have both the mass and radius of a planet. I think the future of exoplanets is really going to continue in this direction. You may have heard that Kepler spacecraft, after being given money to continue for a few more years, then broke and can now not point very well. However, the K2 program found that if it points in the plane of the ecliptic, it can actually still do quite well and is going to continue. Additionally, most of the Kepler detections are still planetary candidates. There are thousands of candidates that have yet to be confirmed as true planets, and so that follow-up program is ongoing. Also, the TESS mission has recently passed its next hurdle and is expected to launch. This will look at transits around bright stars across the entire sky, focusing on bright stars so that they can be followed up very well. And when the James Webb Space Telescope is launched a year later, it is expected to be able to do very good characterization of the planets that are found by TESS. So I'm sure you may have seen plots like this in the past. This is just showing the orbital separation of the known exoplanets and the planetary mass, with both of these axes on a logarithmic scale, with our own planets in the solar system shown for reference. And so still, the current status of this field is that most of the planets that we know of are still much bigger and much closer to the stars, to their stars, than the planets in our own solar system. But as technology improves and as we spend more time looking, we'll eventually push our way down into finding things that look more like our own solar system. And then on that last plot did not have all of the Kepler planets. In this past February, the Kepler team announced the confirmation of over 700 candidates to actual planets. And this is a plot showing now the orbital period and sizes of those planets. And one of the really exciting results of this is that there is a large number of these planets with radii that sit between Earth and Neptune. So these are planets that are very common, but we have no example of them in our own solar system. So these are a relatively new class of planets that have been discovered. One of the unexpected things when you compare some of these systems to our own solar system is how tightly packed they are. So if you've ever done a model of solar system, or if you've ever been to the one, there's one downtown just outside the Air and Space Museum, you know that there's a lot of space between the planets in our solar system. In contrast, we find a number of multi-planet systems in the Kepler field, for example, with Kepler 11 being one of the most extreme cases, where you pack a whole bunch of planets really close to the star. So these 5 planets are all orbiting closer to the star than Mercury does in our solar system, but these are all larger than Earth-sized planets. What this means is that as these planets are orbiting, they feel the gravitational interaction of these other close planets in the system. And one of the cool things about that is that it changes the timing of their transits. So instead of happening exactly periodically, they sometimes occur early or late. And by modeling these gravitational interactions, you can actually measure the masses of these planets that way and confirm that these are indeed planets and not one of the myriad of false positives that you have to worry about in the Kepler data. I also told you that if you have radial velocities, that you can have them both mass and radii of planets. And this opens up the door to being able to get some sense on the composition of planets. And the way this generally works is people build a model of the possible internal structure of the planet, where you can have a core of, say, iron in the middle, surrounded by a mantle of rock, like we have here on Earth. And then you can add envelopes of lighter material, including volatiles such as water and ammonia ices and other types of ices. And then in the last layer, you can also have a hydrogen and helium dominant atmosphere. And the idea is to mix and match the ratios of these various components to get different mass-radius relations. And if you have more contribution from things higher up in this list, you end up with larger radii for a given mass. And as you add more things from the bottom of this list, you tend to get smaller radii. So to put that into action, here's a plot showing the mass and radii of a sample of transiting exoplanets. These non-blue colored lines are showing models that are some combination of core plus mantle, but no envelope. And you can see that there are a number of planets detected that we could then call terrestrial-like, because they have these sort of core plus mantle dominated abundances. But you can also see that there are a number of planets that are not fit with these models until you start adding an envelope of, in this case, 100% water and combination of ices. So these planets right here, you require a large amount of, say, water. And so these have led to the press releases of these water worlds that we've heard. We don't have examples of these in our solar system. Uranus and Neptune, you can see, are sitting above these lines. They require the addition of much lighter elements, a hydrogen and helium-dominated envelope, which you can see has now been added to these models here. So you can get anywhere from a very terrestrial, rocky-like planet all the way up to a Neptune-like gas giant and everything in between with these planets. Transiting systems also let you get a handle on the atmospheres of exoplanets. So when you think about the planet crossing in front of the star, you have to remember that there's also a layer of atmosphere that the light can pass through. And depending on the wavelength of light, the atmosphere can look either transparent or very opaque. So here on Earth, for example, our atmosphere is very transparent to visible light, but in particular for things like ultraviolet and X-ray, thankfully our atmosphere is quite opaque. So if you had eyes sensitive to that, our planet would look bigger than it does if you look at our planet in the visible spectrum. So in practice, the way that you can try to get a handle on the atmosphere is by measuring the transit signature in a large number of different wavelengths. So in this example, this is focusing on infrared wavelengths. And so you measure the transit depth in each of these. And if you have more or less absorption in some of these bands, the radius of the planet will appear larger or smaller. And then you can take these points, which are now represented by these black points here, and compare them to different atmosphere models. In this case, it's comparing to atmospheres of carbon dioxide-rich, water-rich, or methane-rich, none of which fit the data. This spectrum is actually quite flat, which is something that's seen quite often in exoplanets. And these flat spectra, unfortunately, are telling us that there are high-level clouds or hazes that's unfortunately not letting us see deeper into the atmosphere. However, there are other systems that have claims of detections of various species, including the alkali elements potassium and sodium, hydrogen, as well as a couple of different molecular species. Additionally, you can get a sense on the weather on the planet. So when I've talked about these light curves, you might have been thinking that you're basically seeing only starlight, which is relatively true, but there is both the light from the star and the planet there. And so if you work in the infrared in particular, and if you have a very hot planet, what you're really seeing is a combination of both the starlight and the planet's light. So this is a light curve for a very well-known hot Jupiter planet, where the brightness has been normalized such that the star level only is at 1, so everything above 1 is light due to the planet. And what you're actually seeing here is the variation in light due to the fact that you're seeing more or less of the day and nighttime contributions from the planet. So phase 0 is where the main transit occurs, where this planet is blocking the star. And then when the planet goes behind the star half an orbit later, you see a secondary eclipse as the light from the planet is completely blocked. Now, the way this diagram is drawn, it's illustrating a scenario where the planet is brightest basically at noontime, and when the planet is darkest basically at midnight on that planet. But you can see in this light curve here, the peak of the emission and the trough of the emission are actually shifted somewhat from the 0 and 0.5 phase. And when you fit a model to this, you get a couple conclusions. From the amplitude of this variation, you can get the temperature of the day and night side. And from the shift of the peak and trough, you actually find it has an eastern hotspot. And the way you want to think about this is that the planet is not hottest directly at noon when the sun is overhead. It's hottest at an eastward point, or in the afternoon, just like it is here on Earth. Transits also let you measure, yes?
Sorry, how do you know if the planet is rotating on its own axis or not? Like, how does it fit into this?
Yeah, so from this directly, you wouldn't have that information. So there is the possibility that you have either the atmosphere can have high winds that could be different from the planet's rotation. This one, I think, might be close enough that you assume it's tidally locked, but it's not something that you would know for sure. With transiting systems, you can also get a measurement of the alignment or misalignment between the stellar rotation axis and the orbital inclination of the planet's orbit. And the reason why this happens is if you're monitoring the velocity of the star as the planet is transiting, all stars rotate to some degree, which means that one hemisphere of the star is going to be slightly blue shifted and the receding side will be red shifted. So in the case of an aligned system, when the planet transits, it will first block out light from only the blue shifted side of the star, which will cause a velocity anomaly to be red shifted. And then as it crosses the star, it then blocks the red shifted hemisphere, causing an apparent blue shift in the star's light. So you can imagine that if the planet is crossing in some other direction, for example in this one, it may only cross the red shifted side or the blue shifted side, leading to a different type of velocity anomaly. And so this has been measured for a number of exoplanet systems. And at first, we found that exoplanets seem to be aligned, which seems to make sense. That's what it is in our own solar system. The sun rotates in one direction, and all the planets go around in the same direction. But as more of these measurements came about, we find that a number of exoplanets tend to be very misaligned, which is somewhat surprising. Okay, so I finally want to get onto a number of unsolved problems in the field of exoplanets. The first of which was an answer when I asked this to one of my colleagues, is that of planet formation itself. The spin-orbit misalignment that I just talked about, for example, was not expected to be found. We thought we knew how planets formed. Things collapse, spin a disk, and things all go around the same direction. But there are two other big pieces that I wanted to point out. As Nick pointed out earlier, we thought that things built up quite nicely from small things to big things. You dump some gas on it, and then you're done. But it turns out, although we know how to build up small particles up to about pebble size, and we know how things about a kilometer size and bigger can hold together gravitationally, we actually don't know how to get from this step to this step. Because once you get to about a meter, you start to smack into things really hard and break them up back into smaller things. So this step is actually unknown. And the other big unknown has to do with these directly imaged planets, where you have very massive planets orbiting very far away from the star. So whether you're thinking of core accretion or disk fragmentation, how on earth is the disk massive enough to form something so big so far from the star? There's also a problem on understanding the relevance of host star metallicity. If you look at the distribution of metallicity of stars, of planets detected around main sequence stars, shown in this green histogram, compared to the sample that you were observing it from, you notice that the planets are preferentially found around metal-rich stars, which we think makes sense because metal-rich stars have more metals that can build up planets more easily, so that's all fantastic and great. But when you repeat the same experiment on evolved stars, giant stars in particular don't show this trend whatsoever, which doesn't make any sense because presumably these main sequence stars are evolving to subgiant where you still see this trend, and then they become red giants and suddenly the trend disappears, and we don't know why. Tidal interactions is also a very large uncertainty. We think it's very important for a number of processes that are important for planet formation. So just a quick overview of how tides work very quickly is that if you have two massive bodies close to each other, it becomes important that the gravitational attraction felt on the near side of the body is actually stronger than that felt on the far side. So in this case, you have a planet raising a tide on the star, but you also have the case of the star raising a tide on the planet. And then when you have a planet orbiting a star, the planet is orbiting usually at a different rate that the star is rotating. And unfortunately, what happens is that the tidal bulge never is capable of staying completely aligned to where the gravitational pull is trying to pull it. And there's a quantity that we use to describe the lag time between where the tidal bulge is and where the tidal bulge wants to be. And there is a Q basically for both stars and planets, which encompass a whole lot of physical processes that I don't even have remotely enough time to begin talking about. But the basic nutshell is that both of these values are very poorly constrained. We have some observational evidence of them, but even when we think we do, the answers don't make sense. And these dictate how quickly many of these key processes occur. You may have heard of the quantity eta Earth. This is the shorthand for one of the holy grails of exoplanet science, which is essentially to find another Earth around another sun in the habitable zone. And a number of groups have tried to calculate eta Earth, and their results sometimes agree and sometimes don't. But what I'd like to point out is that this is the most recent set of data available to do this kind of calculation. And you'll notice the red points are the data that are available, and you'll notice the point of actual Earth for which we have not yet found another example. So all of these numbers are extrapolations trying to figure out how many of these other Earth-like planets there are. And then I think once we figure out what eta Earth is, the next step is going to be what is eta solar system, because when people start thinking about habitability, there are all sorts of ideas of whether or not you need a Jupiter in your system to protect life from comet impacts and a whole other host of possibly important phenomena. And then finally, I'm glad I talked fast enough to get here, because this is my favorite topic and what I like to work on, is the fate of exoplanets around red giant stars. So we know that we expect many of the planets to be destroyed by their stars when their stars evolved. So this is the same plot that I showed you earlier, and what I want to show you to scale is the size of an evolving red giant star compared to where these planets are. So without even accounting for tides, which are relevant and will pull in even more planets, we know that all of these guys are going to be completely toast because of their stars. And so what I'm interested in is trying to see if we can find some indirect evidence of this destruction. In the population of red giants, we know that they are generally slowly rotating and depleted in lithium, but you can find unusually fast rotating giants and sometimes enhanced lithium abundances. And so this is just an illustration showing a range of lithium abundances and rotational velocities for a sample of giants. The lithium abundances, unfortunately, there's a wide range, which is the bane of my existence. But what I really want you to focus on is that if you look at the average distribution between these, the slow rotating stars and the fast rotating stars do seem to be lithium enriched. And you can explain that if you drop a couple of planets into them. But there is also evidence that planets could survive. In particular, the Kepler-70 system was the discovery of a few rocky planets orbiting a subdwarf. Now, basically what a subdwarf is, if you take a red giant star and knock off its entire atmosphere, leaving behind the core of helium, that's what a subdwarf is. And the explanation for this system is that these rocky planets could not have survived inside the red giant star. However, if they were once Jupiter-sized planets orbiting a normal red giant star, when the red giant evolved, the planets go inside the stellar envelope. The planets get stripped of their atmospheres. But the orbital energy that gets deposited into the stellar envelope can help drive off the red giant's atmosphere, which is quite tenuous at that point. So that what you end up with behind is the core of two planets orbiting the core of a star. So that's pretty cool. I just wanted to wrap up by saying, yes, you had a question.
Question on the lithium ions.
Yes.
Graph. So why don't you see a more continuous distribution as you go along graph? Would you expect the orbital angular momentum that was dropped into the stellar rotation to be more continuous as you go along graph?
You might. That is actually a very it's something that you might expect to see, but there's also some reasons why you may not expect to see it. One of the reasons why you may not expect to see it is that although it helps the argument, you should probably ignore this star here. There should be a limit to how high you can get the lithium abundance if you're adding something as small as a planet. So you would expect to see some sort of top-off here. And actually, in this plot, if you take this star out, it doesn't change this average abundance very much, which I talked about in the paper because of that reason. This one is actually hard to explain with a planet. But if you're adding a planet-sized thing to a star, you sort of asymptotically approach a value, and that's why. OK. So then my final conclusion that I wanted to point out is, again, I think the exoplanets is really a technology-driven field. And we're going to be finding, as technology improves and as we spend more time looking, we're eventually going to find our solar system or another version of it. But I think when we do that, we're also going to find many more things that we've never even dreamed of, because that is basically what has happened for the entire time that we've been discovering planets. So I'll end there. Thank you.
Any questions?
Yeah.
I noticed in the plot where you were talking, we had the orbital angle plot based on the orbital plane of the star.
Yeah.
I thought I saw something at like, you
Boop.
way high at 180 degrees.
Yes. Yeah, so retrograde.
Yeah, that's crazy.
Yes. And so this one doesn't have all of the newest ones, just because the ones with all the newest ones were overly complicated. There are actually very few, you notice,
Yeah, I know this.
at the sort of polar.
Yeah, there's a split. So on the north end of the split, like the 120.
So
Naively, you would think that would maybe be not very stable. I can't picture in my mind how that stable was.
Right. So I'm not very. I don't work in dynamics very often, but my understanding is that once you get past 90, it's actually easier to stabilize to 180 than it is back down to 0. So if I think you can get kicked over 90, you might the dynamics might work to pull you to 180. I'm not 100% sure, but I think that's possible.
No, I see what you're saying. Just like the several up there that
Yeah.
are like are. Okay.
Yeah, and that's what people said when they discovered it. They're like, wait, did we get our signs backwards? No, that's the way it works.
I think there are moons that are in retrograde orbit too in our solar system, so I think it's a similar. That could look as a capture process.
Yeah, I was gonna say I thought those were captured.
Yeah, so I don't know if these are the same source, but
Yeah.
Okay. Any other questions? Then let's sing.
Oh, there's
Yeah,
one
yeah.
more.
Okay.
How stable are the systems that have multiple large planets close to their star? Do you think that some of the planets would be kicked out by the others?
Yeah, so that argument is used actually to say why they're not stars in the background and why they're actually planets. I don't know any of the numbers off the top of my head. I think most of them are stable, relatively stable, but I assume some of these will probably get kicked apart eventually. Is my best guess.
I think some of them are on like M-class stars, so they can have much more compact architectures.
Right.
Okay, thanks for the nice discussion. Thank you, Jillian.
So our next speaker is Brian X from the Goddard Space Flight Center.
Let's see, there's one thing here. Does it fit? Uh-oh, this could be a problem.
If it doesn't fit, you can use mine.
I should have brought mine. No, you did.
I think mine's the same.
I've got the... Oh, it fits.
I'm sorry.
Let's see. Where's the,
Pointer? It's here. Oh, it's not very sensitive, so if you put it in your collar, that's probably ideal.
find the laser point. That's there.
Pointers here.
How's this? Good. Oh. Oh boy. Set control. I forgot the shortcut. Full screen. All right. So thanks, Jolene, for the introduction to what I'm talking about is high contrast direct imaging of exoplanetary systems. Not just exoplanets, but as Jolene mentioned, we're also interested in how planetary systems form and evolve. That's something that we can address with direct imaging. So I'm working on a system called the visible Knowing coronagraph. It's one of many techniques that's being developed to directly image exoplanets. I'm doing this work with several folks at NASA Goddard. I'm a postdoc there. I've been there since earlier this year. And previously, I worked on a similar system that actually, so this system is actually flown in space. It flew on a sounding rocket. I'm not going to talk about that, but if you're interested, feel free to get in touch. So here's my outline. So the challenge in direct imaging is one mostly of contrast. So this is an easy plot you could make yourself showing basically reflected light, combined reflected light and thermal blackbody contributions to the fluxes from solar system planets compared to our sun. And then there's also a hot Jupiter mixed in here to show you what the difference in contrast would be for these systems, of which there are several that we know about. It's probably hard to read the logarithmic numbers over here, but basically the contrast that we're working with for an Earth-like planet compared to the sun in the visible is over here, infrared over here, is about 10 billion to 1. So you don't have detectors that have that sort of bit depth. We've got to block out some of the starlight in order to limit scatter. It's diffracted light that goes everywhere in your system that essentially washes out the planets at small angles. So contrast at 1 billion to 1, 10 billion to 1 is what we're going for with Earth. Jupiter, it's a little bit better. It's about 1 billion to 1. You can go to longer wavelengths where you've got the thermal components that reduce contrast between the planets and the stars. But then, of course, you need a proportionally larger aperture in order to resolve the systems. So we're looking to basically get into the region. So this is an image you're probably familiar with now. This is the Fomalhaut system. There's a planet that's sort of contested out here at about 140 AU. that's thought to be shaping the Fomalhaut debris ring here, this massive ring. So it's a really neat image. This is a Hubble image, so there has been a space-based detection of an exoplanet, but it's not exactly solar system-like. It's way out here. We want to get in here, inside of about 10 AU. So basically every time you see a debris disk image, you tend to see an occulted spot here in the middle. It tends to be about an arc second in extent. We want to be inside of that. And there are future missions following Webb. Webb will do some improvement to the planets that we directly imaged. Right now, all of them are relatively low contrast, so the few dozen that have been directly imaged, they're low contrast, tend to be self-luminous, and then also in wide orbits. But a couple of decades down the line, we're hoping to launch this thing called Atlas, the follow-on to James Webb, which would be a 16-meter telescope, and get us well inside of these occulted spots. So the challenge is how do you suppress a starlight? There are a few different techniques. One way to do this is interferometrically. You destructively interfere the starlight with itself. So light's an electromagnetic field, right? You split it apart in an interferometer. I can do a little dance. You've got light coming in. My thumb is one polarization component. My fingers are another. You split the light apart. In one arm, you flip about X. In the other arm, you flip about Y. You can do this geometrically. You can do this using polarization. And then you recombine, and you've destructively interfered the starlight. So the visible knowing coronagraph, the VNC, is a shearing interferometer. It puts a transmission pattern on the sky that looks like a bar pattern in monochromatic light. If you've got two shears, then you get an overlay of two bars, and you get this sort of pattern here. And then if you change the shear, you can gradually fill in the transmission on the sky. And then also, you can, if you just have a single shear and you're fixed in that shear, you can also roll your instrument and gradually fill in transmission everywhere in the sky. Whereas if you were just staying fixed at one angle, you might be putting destructive interference on top of something that you're interested in looking at. So this is what the transmission pattern looks like on the sky. It's a function of aperture size, wavelength, and the amount of shear in your system. So the science that we're hoping to do eventually is, well, the holy grail is looking for biotracers. That would be pretty neat to find. We want to answer the question, are any of these planets habitable? This is long-term stuff. Once we find that it's habitable, well, what do we do now? Then also making maps. Eventually, you could have you need quite a bit more resolution than even the 16-meter concept that we're talking about gives you in order to spatially resolve continents, oceans, and then look at, say, dynamics of clouds. Clouds change all the time on our planet, and you could expect them to do the same elsewhere. And that would affect then the sort of spectral measurements you might make on planets. This is showing a Jupiter and how it might change if it were in an eccentric orbit, where it's at 2 AU here and then 0.8 AU here. There's quite a bit of difference in the albedo, the spectrum that you see when it's near into its parent star versus further out here. So precursor science that we could be doing in the near term is to bend this down. This is higher resolution than we can really do, given the few number of photons that we're actually getting from planets. So there's a well, you can do it as a homework problem, but for a 16-meter aperture telescope with a 25% efficiency, which is that's optimistic. You're getting something like 100 photons per second when you bend it down to 40 nanometers in the long end of the visible spectrum. So 100 photons per second through to the detector plane, then you spread that out on your detector, and you have to worry about things like your detector noise, read noise, thermal noise. All that stuff is really confounding your ability to detect these objects and do good science with them. But you can do it. Like I said, we flew a sounding rocket that was trying to directly image Epsilon Eridani. The other issue you have to worry about, though, is then debris disks. So this is something that wasn't as appreciated before when early on trying to sell the idea of going to directly image planets. Back up for a second. There's a expression for here determining the distance at which you go from observing planets to observing debris disks. Debris disks are diffuse, and so if you have lower resolution, basically per resolution element, you collect a lot more debris disk light that would be competing with your planet. So you want to have a large aperture to spread out that signal and not compete with the planets. And if you run through, again, using these at last numbers, 16-meter aperture and working the visible, the cutoff is about 20 parsecs, where beyond that, you're looking mostly at debris disks. So we can really only target nearby stars. And that's true also because, again, there are just so few photons, so 1 over r squared, you're really not collecting much light. There's some pretty hard limits to where we want to look. Given that it's going to be hard to get to these places, looking at nearby targets is probably a reasonable thing to do anyway. So we're not just interested in what's going on with the individual planets, but also what's going on with the system as a whole. Debris disks, dust, what's happening to these systems early on when they're still in the formation stages. So here's the Epsilon Eridani system. It's one of the high-profile systems. Others are Beta Pic, Vega. This is what the dust. The dust disk around Epsilon Eridani looks like at 350 microns. Again, we want to zoom in, get much closer into the parent star so we can look for inner solar system-like objects. Interesting thing about this system too is models predict right now. So typically you're modeling these systems by SED fitting. So you've got continuous spectra at shorter wavelengths, and then photometric data at longer wavelengths that you fit to try and say something about the dust distribution, the size, the constituents, and then where it all is inside the system. By direct imaging, we can constrain some of the model parameters and address issues like the possibility of this Epsilon Eridani B crossing the inner debris disk. So there are several architectures that are being considered for direct imaging in the future. Lots of suppression techniques favor an unobscured aperture just because of the nasty effect of diffraction when you have apertures that are more complicated. The nice thing about the visible Nolan coronagraph is that it addresses, or it works well with an arbitrary aperture. So basically, dream up your favorite aperture. We can make that work by virtue of the fact that it works in a pupil plane. So a few of the so this is the at last concept. It's favored as a 16-meter hexagonal array with 3 rings. This is the W1 AFTA telescope that will be that may have a coronagraph for exoplanet science included, and that's actually there's been a down select now. The VNC, the visible Nolan coronagraph, is not among those that have been chosen to go forward in concept studies should a coronagraph be included. But you get more limited performance with this aperture with these other chronographic methods that have been selected. So the science really will be limited. It'll be more than what we can do now, but it won't quite reach what we're ultimately trying to get to perform spectroscopy on terrestrial exoplanets. This is what the VNC looks like in the lab. So the interferometer cavity is here. So there's a source here. Like it's split apart at this beam splitter here, and then it goes into 2 arms before getting recombined. You've got this W layout in order to minimize the angle of incidence, reduce the projection effect onto the deformable mirror. All these systems require deformable mirrors. So these are used not in the, you've got a question?
Yeah, just about the Astro architecture. So is there a reason why those are preferred? Because they're easier just to get up into space?
Oh, it's limited fairing. So anything over an 8-meter. So one concept for Atlas is a monolithic primary, but then it's actually getting the large telescopes into space. So like JWST is unfolding at last is kind of baselined off of JWST. It would also fold inside of a fairing and then unfold once it reaches its orbit. And then I guess while I'm back here, this sparse aperture type of architecture would be good for doing a really long baseline, even going to formation flying where if we wanted to make maps in the future, you really do need the long baseline, and so you could imagine doing something like this. Like I was saying, there's every one of these systems uses a deformable mirror, not for conventional AO where you're trying to take out atmospheric effects on the ground, but rather to take out instrument defects. So no optic is absolutely perfect. And furthermore, when you're trying to match wavefronts or mitigate diffractive effects, you have to do this on a sub-angstrom scale. So really you're playing around with the wavefront on a subatomic scale. So you have to have these, and this is just I don't really have time to go through the whole thing, but this gives you an idea of the scale of the instrument. It of course needs to be packed down, and that's what we'd like to do. That's one of the things we'd like to do next, is make this more like a facility class instrument, or something that we could even potentially fly on a balloon, or probably not a sounding rocket. We really want to get to something where we've got more observing time rather than the limited 5 minutes you have on a sounding rocket. But we do these tests in vacuum to get to really high contrast. You need to do that, not in a hard vacuum, but just enough to take most of the air out, take away air currents, so that you're in a really stable environment. Once we're all done with the first demonstration, getting to the contrast we want, this is what the PSF ends up looking like. This hexagonal PSF is an artifact of the layout of the DM. It's a hexagonally packed segmented DM. And then these are side lobes here of the central PSF. This is a log scale plot of the PSF. And you can play around, you can optimize the solution for the deformable mirror to give you these dark holes, so added contrast where you'd want to look for, you'd like to put a planet and get 10 billion to 1 even higher contrast if possible, in order to get all the spectroscopic absorption features, not just being able to see the planet, but when you disperse the light spectroscopically, you want to be able to actually see the features in the spectrum, so you need higher contrast for that. So this is where you'd want to put the planets, inside this dark hole. So this was a monochromatic demonstration. The next demonstration we want to do is broadband. How am I doing on time? I'm out? I'm out. Okay. Well, so the next thing we want to do is do this broadband. We're going to do this using polarization optics that are coated. So Fresnel ROMs are half-wave retarders. We want to put coatings on them in order to make it a broadband 40 nanometer demonstration and do an order of magnitude higher contrast than what the slide I showed you previously, where it was a 10 to the 8th contrast over 1 to 4 lambda over d. So just outside the core of the PSF. And we've got to do wavefront control and fit in the broadband step here, which is positioning these ROMs very carefully using PZTs. There are 4 of them. And then in the future, because we want to, the big selling point of the VNC is that it works with arbitrary apertures. We want to actually demonstrate this in the lab too. This is something that no one's done. Typically, all the high contrast demonstrations so far have been using very stable, clean wavefronts, so unobscured optics. Low diffraction optics, and then in very stable environments. We want to make things a little bit more unstable and mess up the wavefront and show that we can deal with that. Thanks.
Thank you. Big questions? I have one. I see that you're trying to put the things in space, right? Is it possible to do something from the ground?
There are efforts from the ground. So GPI, the Gemini Planet Imager, is a notable one. Ultimately, it's thought that the contrast limit that you're going to hit is about 10 to the 8th. And so you won't be able to get to the narrow separation angles you need to get get exo-Earths just because of having to keep up with the atmosphere. From space, you don't have that dynamic atmosphere problem. Everything's relatively stable. There are still things you're worried about with instabilities. They're slow, but the heating from changing the payload orientation relative to the sun, this is why James Webb has these massive shields, not for protecting the structure so much, rather keeping the optics cold, right? It's infrared. But in the future, when we're looking at optical wavelengths, it's not so much keeping the optics cold, rather just keeping the mechanisms and the structure stable. So going to space is kind of where we need to be.
Okay, thank you.
So next speaker is Prabal Saxena from George Mason University.
Just right.
Wait a second. Is it Mac or Windows?
It's it should be PowerPoint. I also have a PDF. Is this too close? I talk pretty loud, so.
Keep it close. That's good.
I'm a little worried that I'm. All right, there.
Yeah, you're
I'm gonna blur your ears out. Take Alex's eyes out first. Yeah.
So,
Yeah. Let's hope it doesn't break.
which one?
The PowerPoint. Over here.
There you go.
All right, excellent. So my name is Prabal Saxena. I'm a graduate student at George Mason University. What I'm going to talk about today is a very specific type of exoplanet, so these very close-in rocky exoplanets. And what we're really looking at is some of the unusual dynamic processes that are going on these exoplanets. So the general title that I have here is a simple estimate of mass transfer on tidally locked heated super-Earths. That's a lot in there. I'll try to unpack a little bit of it, and then I'll talk about why we're doing this simple estimate of mass transfer and what that might mean once we start to do a more complicated model. So I'm going to skip through this slide really quickly because Dr. Karlberg did a great job talking about the fact that there are a lot of exoplanets out there. They're very diverse, and there are a lot of missions that are going to go characterize them and detect them. I do want to mention that she talked about K2. We're also going to have TESS, Plato, and Gaia that's going to fill in far more exoplanets that we're going to see. A lot of these are going to be looking for transiting exoplanets, and those are biased towards close-in exoplanets. So obviously, if you have something that's transiting on a short orbit, you're going to see far more transits of it. You're going to be able to characterize it more easily. So the planets I'm specifically going to be talking about today are, again, it's a very similar graph to what Dr. Karlberg had, where you see these planets that are basically small enough that we consider them to be terrestrial once we actually are able to constrain their densities, and that are close enough in terms of their relative habitable zone that they're very, very hot. We're talking equilibrium temperatures that are above 1,000 degrees. So in these particular cases, and she alluded to this a little bit, and there's a little controversy on it too, there are actually estimates and equations that talk about the tidal locking radius based upon stellar class for different types of planets. So this is a function of a bunch of different parameters. But in general, there are estimates that you can make, which is why people assume that certain planets that are really close in are tidally locked. We're going to assume for the planets that we're looking at that they're tidally locked. There was a paper about 2 or 3 years ago that talked about how a lot of these planets might actually be in higher order resonances. But that was actually by Framsky and Makarov. But we actually talked to them, and it turns out now that they've learned that there's higher tidal dissipation in these interiors, and you see some type of partial melting, some of these planets are likely to fall into 1-to-1 resonance. So I'm just kind of setting the stage for what we're talking about here. And I'm going to talk a little bit more about what exactly these terrestrial exoplanets are like. The reason why they're interesting is because they're so close in, because we're getting a lot of data on them, we can actually use them as laboratories where we can test kind of celestial mechanics, where we can test atmospheric, dynamical processes that you wouldn't otherwise see in our solar system, or especially on Earth. These planets tend to be between 1 Earth mass to 10 Earth masses. We have a conservative assumption that they're at least the Earth's bulk density, or they might be kind of higher. You might have had volatile loss of lighter elements. So what you also expect to see is if they're tidally locked, you expect a really, really high contrast in temperature from the day side to the night side. Due to that contrast, and due to the fact that the day side is being irradiated quite heavily, you expect to see substellar magma oceans, and you also expect to see potentially mass advection across the terminator as some of the material on the day side is being sublimated. So what we're going to explore, this is actually something that you can see in our solar system as well when you look at Mercury and you look at cooler analogs. But what we're going to focus on is really the mass advection that we expect to be going on in these particular planets. So here I just wanted to show basically the types of surface gravities and densities you'd expect for these different super-Earths. You can see they vary pretty considerably. If you're a planet that's been engulfed by a giant star, then you're going to expect to see maybe a remnant iron core, something like that. It might not apply as much. What we're really talking about is silicate mantles that are being exposed that don't have a significant envelope around them. And these things are believed to exist because in a lot of cases when you get close in enough, the hydrogen-helium envelopes, they have escape times that are pretty short. So what you're really left with are just really thin atmospheres that are due to the sublimation vapor pressure of alkali elements and metals. So the advection rate. So before I start talking about it a little bit more, advection, really what we're talking about in this case is just the bulk movement, the bulk transport of mass from that day side past the terminator to the night side. And you might talk about, well, why is that interesting? There are a number of reasons why we think it's interesting. One is that if it's happening fast enough, you're having a large-scale resurfacing process, which might basically change albedos in the surface, which might cause gravitational deformation, which can actually lead to a resultant gravitational effect in terms of rotation. So that's the reason, that's really what's motivating what we're doing. So the first thing we wanted to do was calculate a basic advection rate for these planets and say, well, how fast is this stuff moving? Is it moving fast enough that we care? If we have, a couple thousand kilograms over a billion years, I should go do something else for my PhD. So in this particular case, we said, all right, in terms of advection rate, what we want to do is we know it's based on a couple of really simple factors. And this will be kind of intuitive to you. One will be equilibrium temperature, or specifically temperature at the substellar point. Another will be what the value of your surface gravity is, and then what your volatiles are, what your atmospheric constituents are. Finally, it depends on the surface area of your planet. So if you have a big planet, you have way more stuff, you have way more material that needs to be transported. So the rough idea was obtain basic atmospheric values for pressure and density, find those profiles based upon the latent heat of sublimation for your expected constituents. And basically what we did was we used results from a Yamila Miguel paper, which is also, she worked with Schaefer and Fegley on these chemical models of vaporization of these heated Earths. And we tried to find what exactly the latent heat of sublimations were so that we could kind of extract the atmospheric pressure from these. So I have that in the next slide. And you can see the really important things to notice, unsurprisingly, that you need to go a little bit past 1,000 degrees to start to see any of these things start to vaporize. As you start to go towards higher temperatures, until you hit almost implausible temperatures, I shouldn't say that because at this point we're finding planets with equilibrium surface temperatures that are getting crazily high, you have sodium as the dominant constituent. So what we did is when we're going to start to model these things, we modeled these advection rates for all of these different constituents. Well, we started off with sodium because sodium has obviously a 1 or 2 order of magnitude higher atmospheric pressure. So I already talked about whether it's an interesting problem, and that's why we're kind of running and trying to find these maximum advection rates. So our idea in terms of doing a very, very first cut rough model of how much you're actually advecting to the night side is say, all right, your export rate is just going to be equal to the total material transported across the terminator in a column of mass given by a scale height. So we assume that the velocities are generally approximated by a sonic velocity and that the temperature profile that you're applying to the day side is actually Lambertian until you get to a point where you typically have something, I guess, about half of the temperature value that you'd expect from the substellar temperature, substellar point. At that point, we took a linear fit down to what you expect for the night side, and we just basically integrated the mass over that particular area. So these are going to yield the most optimistic and almost certainly unrealistic values in terms of your advection rate. What that means is that the bulk transport that you're seeing is going to be higher than what you'd in fact expect if you gave it a more sophisticated treatment, but it'll tell you whether or not this is an interesting topic, whether or not this is an interesting problem to pursue. So here, these are a couple of graphs for different types of atmospheres, and one of the things you'll notice is that in each of these cases, once you get to about, so to give you an idea, Coro 7b, the substellar point, you expect that temperature to be about 2,500. At around that point, for just about any type of Earth radii with a variety of different surface gravities, you see something where you have about 10 to the 12th to 10 to the 14th kilograms per second that's being advected over the terminator. That's a little bit hard to comprehend in terms of what that means over a certain amount of time, what that means in terms of how much mass you're actually moving of the planet. So just to kind of figure out, well, what's a rough estimate? So if I assume that one of these planets is tidally locked, if I assume that Coro 7b is tidally locked, which is something I think most groups do assume, and I say the equilibrium tide on Coro 7b is equivalent to basically the equilibrium tide you'd expect for a planet with a rigidity equivalent to the Earth's. So the equilibrium tide is something like 90 kilometers. If I assume that there's a cap on that day side, which is a 90-kilometer cap that runs from the terminator all the way through, the amount of time it takes to advect that entire cap would be something like 1.4 years for a sodium-dominated atmosphere for a purely sodium cap, and something in the range of about 300 to less than 10,000 years for heavier constituents. So on the scale of exoplanets and the scale of a lifetime for an exoplanet, that's pretty damn quick. So one of the things you want to figure out then is, if you're having this cap advected this quickly, yes, it's definitely a contrived model. We want to start to figure out, well, how can we start to get a more realistic analysis? How can we start to find what a more realistic timescale is for this advection? So there are a couple interesting things that this brings up anyway, just from this simple estimate. You can see there is a couple order of magnitude difference between some of these constituents. That almost certainly means you have fractionation going on these planets. And if you have fractionation going on in these planets, that's the type of thing where that might show up when you're starting to do phase curves, where you're starting to look at planets that are kind of atmosphereless and you're looking at reflectance. Additionally, this is going to be a pretty good laboratory for dynamics of really, really weird alkali, silicate atmospheres that we wouldn't be able to see here. However, I want to come back to this. What we're going to actually be doing, though, is we do realize that these are unlikely assumptions. These are overestimates. So in order to kind of deal with these overestimates, we're starting to now use these overestimates that still kind of proved that this is a viable project to figure out, well, how do we actually write up a model that's more sophisticated? And the way we do that is we start to take into account surface boundary layer shear issues. So it turns out that these are very thin atmospheres. On average, even at the substellar point, your maximum atmospheres are something like 100 millibars. In some cases, for Coro 70b, it's about 10 millibars. So you see they're very, very thin. In these particular cases, the optical depths in the visible and thermal are much less smaller than 1. So you don't expect there to be significant radiative effects. So what we really need to take into account when we start to do a more, comprehensive model is start to take into account the dynamics of interchange between the surface. So when we do that, we also want to incorporate an accurate temperature, pressure, and density profile on the day side, and then we want to extract from that what the actual deposition rate is, which is actually a really simple function of the vapor pressure versus the atmospheric pressure, which is what we'll calculate with that model. So the model that we're now working on, and unfortunately we're just doing replication studies and kind of testing studies now, is one that follows the work from Ingersoll et al., just an 85 paper on the supersonic meteorology of Io. And what they did there was they solved the conservation equations of mass, momentum, and energy. And they basically parameterized these surface fluxes in a variety of different ways, and they looked at a vertically integrated 1D atmosphere. So when they solved that for Io, Castan and Minu in 2011 actually followed the same methodology to calculate the atmospheres for a couple of this heated super-Earths that we've just been talking about. And they suggested that deposition needs to be explored, which is obviously what we're doing here, because in some of these cases, they're getting atmospheres that are about 10 bars to 100 bars on the day side and go down to basically being atmosphereless by the time you get to the terminator.
So when we've started to actually replicate the results from Castan and Minute, we found very similar results, basically been able to replicate what they've done for Coro 7b. And we've started to find that advection rates are still on the order of less than a couple million years. So that means you can still actually advect away this tidal bulge in about less than a couple million years. So now it's not quite as dramatic as a couple thousand years, but what you're going to be able to see is that as you have this deformation in the shape of these planets, you're going to start to have tidal effects. You're going to have to start, either you're going to have issues such as resurfacing, or you're going to have things where you have such a deformed shape that you might have rotational changes. So these are a couple of really interesting things that we're going to try to explore as we build these models more comprehensively and start to take out really accurate deposition profiles. And hopefully I'll come back here with a couple new graphs that show you how exactly it's being advected away using these models. The last thing that I do want to mention is that when we're looking at these particular models, we're going to put in a more accurate temperature profile too, and take into account latent heat contribution. So we're trying to make this a first-order model where we can actually take into account the fact that when you're this close into a star, the angular size of your star is actually pretty significant in your sky. So that means you have some type of penumbra effect. You can't just take it as a point, as a point model of illumination. So when you start to do that, you start to actually up your advection rate even more, and you start to find that these planets are probably going to have significant resurfacing, even past the extent of their magma oceans. So that means not only are you going to have some type of cycle, like some type of silicate cycle, but you're probably going to have the type of thing where you have serious deformations and serious topography due to these. That's really it. Any questions? So escape. So escape that's a great. I had actually skipped over that really quickly. So if you do just like calculations for Jeans escape timescales or even hydrodynamic escape timescales, even for sodium, the timescales are so far. I mean, they're so long that they generally don't tend to play in terms of like the atmospheric flow. But that is something that when we're starting to do this, we'd want to include that as well, because that is going to drive some small amount of loss. Yep.
I may have missed this, but for your model, is it just a rigid body plus an atmosphere, or do you consider the rigid plus possible molten?
So the model we're doing now, that's a great question. The model we're doing now is a rigid body plus a substellar magma ocean plus that. Because the thing is, if you have something that's cycling back into the magma ocean, or even someplace where you're looking at something that has a high plasticity, where you have a decent amount of flow, you're going to find that it's not going to change. It'll be interesting for resurfacing, but it won't necessarily change the gravitational potential of that planet.
So next speaker is Ting-Ben Lan from Johns Hopkins.
Really? It's okay? Is it too loud? Or okay? So, okay. Wait a minute. Okay, hi, good afternoon. My name is Ting-Ben Lan. I'm a grad student from Johns Hopkins University working with Brice Mona and Guangten Zhu. And it's my pleasure to be here and to present you our recent study about exploring the diffuse interstellar band with the Sloan Digital Sky Survey. So what are diffuse interstellar bands? Diffuse interstellar bands are absorption features with unknown carriers detected in the interstellar medium. And it's kind of one of the longest puzzle in the astronomy. And the story began in 1922 when Hager, she was a grad student observing spectra of stars. And she found that in her stellar spectrum, there are some unexpected absorption features. And she reported the existence of those absorption lines, and without further investigation. And after 20 years later, Muriel and Wilson, they revisited those absorption lines and confirmed that this absorption line arises from the interstellar medium. And after that, oh, by the way, so because most of these absorption features are kind of broad, they are on average broader than the absorption features due to atoms. So at that time, people call them diffuse interstellar bands. And since then, people have been trying to detect all the dips, so all the dips in the interstellar medium and trying to understand the nature of them. And until today, there are about more than 500 dips reported in the optical and infrared wavelength regions. So actually, if you are studying spectra, all of your spectra have these features, but they are just weak and hidden in your noise level. So to give you an example, here I show you a synthetic dip spectrum compiled by using very high signal-to-noise ratio stellar spectra. And as you can see, there are about hundreds of absorption features, and with various properties. Some of them are quite broad, like this one, and some of them are quite narrow. And there's no regular patterns as a function of wavelength. And the reason I say that the nature of them is one of the longest puzzles in astronomy is because after almost a century of investigation, we still don't understand the carrier of these absorption lines. So we don't know they are kind of due to the materials like dust grains or like PAHs or some sort of organic molecules. Until today, that non-single of these absorption are reproduced in the lab. And there are 500 of them, more than 500 of them on the sky. And as you might notice, except a couple of dips, most of dips are really weak. They are all below 1% level, so which makes them really difficult to study. And the traditional way for people to study these dips, they are basically using hot stars as a background, and they obtain a very, very high signal-to-noise ratio spectrum and very high resolution spectra to detect those weak and narrow dips, and trying to understanding the nature and the correlations between those dips and ISM tracers. But our team at Johns Hopkins University, we apply a different approach. So instead of using hot stars as a background and collecting the data by ourselves, we make use of the statistical power provided by large sky surveys, such as Sloan Digital Sky Survey. So Sloan provides hundreds of thousands of spectra with basically three types of sources: galaxies, quasars, and stars. And as I mentioned, basically for each spectrum, they all have the deep absorption features imprinted in the spectrum. But because they are too weak, so basically they are hidden in the noise level. But if we can combine several of them, or combine thousands of those spectra, we can actually reduce the noise level and detect those dips and study the correlations between the dips themselves and the dips with the interstellar medium. And in the following, I'm going to use stars as an example to show you, how we, what's our procedures to remove the intrinsic SED of the sources in order to detect the dips hidden in the noise level. So, yes. So let's start from this stellar spectrum. So as you can see, we have a stellar spectrum. So the first thing we do is to have a model of the stellar spectrum. So we build our own stellar model, and we can basically, for each star, we have a stellar model spectrum. And we model this observed spectrum with this black model spectrum. And we can remove the spectral features from the stars by taking the ratio between the blue observed spectrum and the black model spectrum. then we get a stellar SED removed spectrum. So we already subtract the features from the stars, which left there is a flat spectrum. And the flatness of this spectrum indicates that actually our model can well reproduce the stellar intrinsic stellar SED. And for Sloan, for the signal to noise, for the property of Sloan spectrum, on average, the noise level is about 5% level. So you can see the scattered noise level is about 5% level. And as I mentioned, all of the dips, most of the dips are actually really weak. They are all below 1% level, which means that we need to combine several thousands of land in order to reduce the noise level and get the dips. So here I show you an example. Right now, this is a stack spectrum. So I stack about 2,000 stellar spectra. So as you can see the scale here, so the scale is 1.5 to 0.5. Now the scale here is 1.01 to 99%. And we can actually reduce the noise level to about 0.1% level. And as you already can see, there are several absorption features. There are the dips that I just described. And so we can have a close look about this spectrum. So on the, as you can see on the right-hand side, there are several wiggles, which is actually due to the skylines, both in the emission, some sky emission, and some absorption from the sky. So these features are difficult to remove. So in our analysis, we only focus on the blue part of the spectrum. And if we focus this region, and we zoom in a little bit, and you can see that there is absorption feature, several significant absorption features. They are all the dips that I just described. And notice that in this composite spectrum, I only make use of about 2,000 stellar spectra. But Sloan actually provide like 100,000 stellar spectra. So actually we can detect more dips with a lot of stellar spectra. And here's an example. So right now this is a stacked spectrum with about 40,000 stellar spectra. And the composite spectrum is shown in the black, and this white in the bottom is a synthetic spectrum. And for each blue band are a dip, indicates a dip, which we can detect and characterize them robustly. And for the dashed line are absorption features consistent with a weak or broad dips, which we didn't include in our analysis because they require more detailed analysis because they are broad and we need to kind of estimate the continuum better. So in our analysis, we mainly focus on this the dips detected in the blue band. There are 20 of them. And the gray band shows some residuals due to the stars or the skies, which we cannot perfectly remove. But from this composite spectra, we demonstrate that by using Sloan spectra, we can actually detect 20 dips at the same time, which is like 2 to 3 times larger than previous studies when people are trying to study the correlations. So with our method, we now are in the position to study the dips across the sky. So here I show you a dip map. For each pixel in this map, there is a composite spectrum with signal-to-noise ratio larger than 100. And for that composite spectrum, we can measure the 20 dips I just mentioned. And for the color indicates the absorption strength of the 20 dips together. And as you can see, we already can see some structures. And basically, they are consistent with we found the dust map, for example. So with this dip map, we can actually start to kind of cross-correlate with a lot of sky map to understand the nature of the dips and other ISM tracer. So for example, we can cross-correlate with a dust map provided by the famous SFD. Based on 100 micron emission, we can cross-correlate our dips with the pH emission traced by Weiss 12 micron emission. And we can cross-correlate our dip map with atomic hydrogen traced by 21 centimeter emission, as well as the molecules traced by CO emission provided by Planck. And in the following, I'm going to focus on the result based on the cross correlation between dips and atomic and molecular hydrogens, where we find there's interesting correlations. So we found that in general, there are 3 types of correlations between dips and hydrogen. So here I show you is the atomic hydrogen column density, and the y-axis is the molecular hydrogen column density estimated based on the CO emission. And there are 3 representative dips. And as you can see by looking at the scatter plot, so the color code indicates the absorption strength normalized by the mean of sample just for the demonstration purpose. And as you can see by looking at this scatter plot, you can already see different trends. So for the top dip, in this top panel, you can see that the color gradient increases from the left bottom corner to right top corner, suggesting that this dip, the absorption strength of this dip actually increases with atomic and molecular hydrogen. And for the dip in the bottom in the middle panel, you can see that the color gradient basically mainly from the left to right, indicating that this dip, absorption strength of this dip increases only with atomic hydrogen. And in the bottom panel, you see that the color gradient is from the left top to bottom right, indicates that this dip, the absorption of this dip actually increases atomic hydrogen but decreases with molecular hydrogen. And to further demonstrate these correlations, we can select a narrow bin of molecular hydrogen and look at the correlation between atomic hydrogen and dips. And you can see that all of these 3 dips increases with atomic hydrogen. And we can do the same thing for atomic hydrogen with a fixed atomic hydrogen. Then you see the dependence of the molecular hydrogen and the dip strength. So the first one increases, the second one is basically flat, showing no correlation, and the third one is actually decreased, showing there's anti-correlation. And motivated by these 3 types of correlations, we attempt to use a simple parametrization, use a simple formula to parameterize these 3 behaviors by using a formula including 3 parameters. The first one is the overall amplitude of the dip strength. And then there's a dependence of atomic hydrogen, and there's another dependence of molecular hydrogen. And for each dip, we apply this formula to fit the data and get the best fit parameters. And this is the first attempt to characterize dip with the atomic and molecular hydrogen at the same time. And the results shown in this plot, so in the x-axis, mu is the dependence of molecular hydrogen and dips. So it's the dependence of molecular hydrogen and dip. And the y-axis is alpha, is the dependence of atomic hydrogen and dips. And there's a lot of information in this plot. First of all, we find that the alpha value is all about 1. And it suggests that all of the 20 dips are actually depends on the atomic hydrogen with a similar dependencies. And in contrast, we find a wide range of mu, from the positive on the right, positive correlations, to negative with the negative correlations on the right, on the left. And from this plot, the color indicates the width of the dips. And we find that there's tentative trend showing that the red is showing that the width of the dips are broader, and blue shows the width of the dips are narrower. And we find there is a tentative trend showing that narrow dips are likely to correlate with molecules. And from this plot, we can also learn something about the correlation between dips themselves. So if I select 2 dips, for example, these 2, you can expect that they will have a tighter correlations than the dips between this one and this one, because they have a different dependence with molecular hydrogen. So with this plot, with this new analysis, now we can compare our result from with previous studies. And I just show you a few examples. For example, Kemi et al. In 1997, they studied the correlations between dips themselves. And they found that these three dips have a very tight correlation with each other. And as I said, the distance between dips can also indicate between the strength of their correlations. And from analysis, we show that these three dips are actually clustered together, which consistent with their results. And another study, they classify the dips according to their profiles. So they have some dips found there are some structures, substructures, and some dips without substructures. And again, these two populations are actually well separated based on our analysis, which is consistent with their results as well. And another study, they studied the ratio between these two dips and found there's a correlation between the presence of molecules. And from an analysis showed that this dip only correlates with atomic hydrogen, but this dip actually correlates with atomic and molecular hydrogen at the same time. And the ratio between them will naturally correlate with the presence of molecules, which is consistent with their results well. And finally, Freeman et al., 2011, they did a kind of similar analysis by calculating the correlation between dips and molecular hydrogen and the correlation between dips and atomic hydrogen. And they find like these two dips have a higher correlation with molecular hydrogen, and these two dips only have correlation with atomic hydrogen, which also consistent with our results. So the consistency of our results and the previous studies indicates that actually our measurement of dips are actually quite robust, even though we kind of have a sophisticated procedures to remove the intrinsic spectrum and stack the features together. But actually, we detect the dips quite robust. And it also suggests that we are on the right track to understand the nature of those dips and the environment they can exist. And before I jump to conclusion, I'd just like to mention that in our group, at our group, Johns Hopkins, we are not only using the optical spectrum from Sloan, but also using a near-infrared spectra just mentioned this morning from the Sloan 3 Apogee Survey. A postdoc, NSF fellow, Gail Sasetsky, she made use of those spectra and detect the dips in the near-infrared and use them as a tracer of galactic structure. And in summary, we make use of about 500,000 Sloan spectra with all types of sources and study 20 dips at the same time. And with this, our method, we are able to, for the first time, create a dip map on the sky over 5,000 square degree, and use our map to calculate the correlations between other ISM tracers. We find there's an interesting correlation between dips, atomic hydrogen, and molecular hydrogen. And for the first time, we try to characterize dips with a simple parametrization and reproduce previous studies over 20 years. Thank you.
Questions?
So if I read this plot bottom correctly, the width on the molecular side is narrower.
Yes.
The width on the hydrogen side, atomic side, is wider.
Yes.
Is that right? Is that,
Yeah.
does that fit into a sort of an understanding of why that should be?
So, yeah, so like this study. So in this study, they actually studied the profile of dips. And they found that actually for the narrow dips, there's tend to have a substructure, which suggests that the narrow dips might correlate with some kind of molecules with the rotation energy.
Right.
Then they will have some substructure. So
Those levels are presumably very close to each other.
yeah. So yeah.
Energy levels are very small.
Yeah.
Yeah. Okay. That sounds good. All right, let's thank the speaker.
So our next speaker is Jake Turner from University of Virginia. It's here, right?
Hello?
Hi.
Hi. Hi. Hi, everybody. We're going to go back to exoplanets now.
Yep. So which one do I click?
You can just click the PowerPoint one. They're all the same.
The same? Okay.
Yeah. I just saved them in different formats just in case.
All right. What's that? Okay, that's fine. All right.
Okay, so I'm going to be talking about trying to constrain the magnetic fields of transiting exoplanets through ground-based near-Earth observations. And so, as we heard earlier, we're trying to characterize their atmospheres, magnetic fields, and all the other good stuff. So I've done most of this work at the University of Arizona. It was for my undergrad and research between undergrad and graduate schools. So it's most of that stuff. And these are all the people I've worked with. Most of them were students through Astronomy Club and stuff like that. So as we mentioned before, I'm looking at transite. So you look at the planet outside when it's not in front of the star, and you just have constant, and then you can look at the dip. So I already introduced that, so I don't have to talk about that much. So why do we care about magnetic fields at all in the first place? So you can learn about the internal structure and rotation period. As some people mentioned before, we don't know anything about those. We're trying to get a handle on them, so you can learn about that. Moons, we have not detected moons yet. This is one way you can do that. Io is a good example in our solar system, how you can look at the magnetic field of Jupiter. Habitability, we think if you want to be habitable, you should have an atmosphere with molecules in it and all this other stuff, but then you should have a magnetic field, which is good for Earth and stuff like that. So those are some of the motivations behind that, and just cool to study something new as well. So the method we're using is kind of archaic. So we're studying hot Jupiters that are really close to their host stars, as we mentioned before. So they're basically orbiting about a day or two. So they're 0.02 AU away. If you want to think about it, they're about 2 to 3 solar radii away from their stars. So they're actually so close to their host star, they're actually in the corona of their host stars. So these planets are in a really extreme environment. So as they're traveling around, they're actually going through the coronoplasma. And so if these planets have magnetic fields, this magnetic field is going to interact with the coronoplasma as it's traveling through. And this interaction will essentially create a bow shock in front of the planet. And there was this group, University of St. Andrews, Vidota et al., that proposed that this bow shock can become opaque at certain wavelengths, specifically at near-EV wavelengths. So if you look at the normal transit, you just have this normal, nice, symmetrical transit. You can study it and learn about the atmosphere and all this other stuff. But if you look in the near EV, you have this extra absorption. This is exaggerated, obviously. And so your transit actually looks like it starts earlier, and it's going to have a bigger dip, and it's also going to not be symmetrical anymore. And so they predicted this difference should be about 30 minutes, and you should definitely see this from the ground and stuff like that. So that's essentially what I'm looking for, is this difference. And if you actually observe that difference, you can it's directly correlated to the magnetic field strength. The greater magnetic field strength you have, the greater this difference is going to be. So we're looking for some non-symmetrical transits, basically. So that's kind of the idea. So the observations, we used the 1.5 meter telescope in Arizona on Mount Bigelow. This is a picture that I took while I was taking observations. That telescope, we use a Mod 4K. It's a 4K by 4K CCD. That's liquid nitrogen cold. It's really good for this kind of observations. Really low thermal noise. Will characterize flat fields, all this other stuff like that. Low readout noise, thermal noise. It's pretty good. And so all of our observations, we took. We had a lot of time. I had 120 nights for several years. Not all of them were nice, but that's how much we had. And so our RMS of our outer transit baseline ranged from about a millimag to 7 millimag, which is pretty good. Most of them were around 2, so that was great. Our seeing was pretty good as well. Arc second seeing, so it was pretty good. And our guiding, we had a really good auto guider on our CCD, which is important because if your star's moving around on the CCD, you're going to have a lot of systematics in your data. And if you're trying to look for asymmetries in your data and stuff like that, you want to make sure that's not caused by your instrument. And so throughout all of our observations, most of the time they didn't move more than like a pixel, but the greatest one was 3 pixels. So you can actually see that in your data and make sure it's not in there. And so this is an example of some of the data we have for a variety of different targets, and so you can see the dips in all of them, which is pretty good, right? So we looked at 17 different targets multiple times. We have more transits in this, but this is just a good representation of all the transits we got. The most popular targets that everyone always looks at. And so we created a model, we created a pipeline actually to reduce this data, which was a lot of fun. And then we also created a model to model the transits. And in the model, the original model we created assumes the planet's spherical, and that's what is shown here. And to first order, it actually fits all the planets perfectly. But if you remember, we were trying to look for non-symmetrical transits, so we tried to do a few tests to check that. So we try to use a model that someone created that assumes the planet's not spherical, and we actually got the same result of a non-spherical planet with a spherical planet. This is just an example of TRES 3b, one of the planets we looked at. So there's no difference between fitting the planets that way. We also just looked at the data itself and flipped the data over and subtracted the flipped data by the original data, and you should see an asymmetry if there actually is this asymmetry in the plot. And this is an example of that, which is basically just a random scattered plot. And so all of them look like that. And so we don't actually see any asymmetries within the precision of our data, even though we predicted what we should have. And I'll just show you a zoomed-in plot of one of our targets. I really like this plot. It's a really nice one. So you can see the transit. And so this blue line is actually where we predicted the transit should have started with some reasonable assumptions of the magnetic field of the planet. And you can see, obviously, this is where our model predicts it should happen, the beginning and the end. And then these are the residuals, and then this is the flipping thing I was mentioning before. So you can see there's actually no difference, and it fits really, really well. And so it's a chi-squared of basically 1.
But if you go a couple slides back, there was one which looked kind of obviously asymmetric.
Yeah, so there's a few that actually look like they are, and then you look. So this one, this is WASP 33b, which is actually a variable star. It's a delta Scuti star. And so when we were observing this star, we saw exactly that, and we did all these tests, and we're like, oh, we actually saw something reasonable, and then we looked into it more, and it actually is the variability we see is the variability of the host star. And so you can actually filter that out, but no, I didn't filter that out. I'm not from Light Curve. But yeah, that was an example of something that you have to worry about a lot. And we did observe one system where we thought we saw a possible dip in it, and not quite what we were expecting. So if you assume that the bow shock is clumpy, for example, then you might not see an absorption along the whole bow shock as it's crossing the front of the star. And so as this is the same as before, so we have the blue line is the prediction of what we should have seen, and we saw this little dip right here, and we're like, but that's only 2 sigma, so it's not really significant, but it is exactly where we predicted at. And so then we observed this again, and we actually didn't observe it. So actually it was an unknown systematic, but we checked the pointing, we checked the full max, the weather, everything, and no matter what we did, it still was there. Yeah, question?
So when you were looking at potential candidates to prove this in, are there specific stellar classes where your corona densities will be higher, where it might be more obvious?
So we're basing all of this off of the predictions that the original Vidodo group did, and it's just normal FKG stars. There's some M dwarfs in there, but yeah, so it's basically just normal stars essentially. So they predicted that you should see if you're getting compression enough, you should be able to see some kind of absorption with a normal G star. So we actually think that's an unknown systematic in our data, even though we got follow-up observations, and so that was fun for a little bit. So we can get upper limits on the magnetic fields, assuming this theory is correct. And so these are some of the numbers that are really hard to read, but essentially they're all really, really low. Some are predictions of magnetic field strengths for hot Jupiters are 8 to 30 Gauss, depending on which group. 8 is about Jupiter, slightly lower than this, since some of them are, probably most of them are tidally locked. However, most of the magnetic field strengths we get are 10 times lower than Earth's, for example. And so this is kind of unphysical, and we're trying to figure out what assumption in the model might be causing these non-detections in the first place. And that's actually what I'm working on now for my second year graduate student project. Essentially, one of the things that we think is causing it is there's actually might not be anything in the bow shock that could cause this absorption in the near UV wavelengths in the first place. And so the reason we're not observing this is because